Alrighty, gang, welcome back. Sorry, once I close the door here. I apologize if I'm not 100% my normal self today. The wife and I have had the good luck of getting smacked with COVID through our son's daycare. So rocking a small fever and all of the fun things that come with that, but we're not so bad that I cannot function. So we're going to continue chucking along. It's nice that this is a Zoom class rather than an in-person class. My in-person class has done some pretty radical shifts in the last few days, but we will probably not notice much besides me being a bit more of a mess than usual. You've made it through exam one, so congratulations. If you have not yet taken exam one, obviously I need you to do that. So please, I think I posted an announcement. Make sure I posted it to your class as well. Yeah, read this if you have not yet taken exam one. Right, so if you didn't take exam one for whatever reason, right, if you weren't ready for it and you sent me a message, we already talked about it, then that's great. If you didn't contact me but just didn't come to the exam, that's okay. If something happened, sick, tire flat, whatever, you know, your dog got arrested, doesn't matter why you missed the test. If you missed the test, come to my office hours this Friday. That's starting at 1 p.m. and we will get you set up to take the makeup test. Now, this is only for people who didn't take exam already. If you did take the test and the test is done, it's a different test than the one that that you guys took, that the other part of the class took on Monday. It's not necessarily any harder or any easier. It's just a different test. And there's no like retests or anything like that. It's just for folks that did not or could not take the test on Monday. So yeah, take a look at this announcement if you haven't yet. If that applies to you, please take a look at that. Make sure you come to my office hours Friday at 1, and we'll get you into the makeup test. Today, though, regardless of whether you've taken the test or not, today we are moving into the middle chunk of this class. So this class, I mentioned back on the first day when we went through the syllabus, really can be thought of as kind of having 3 parts. There's the first part, which is all on integration, right? Stuff you can do with integrals and learning how to evaluate integrals, you know, more complicated ones than you see in Calc 1. The second part of this class is all about convergence, and converge is a word that has meaning in the English language, but in mathematics it has a slightly more specific meaning, although it is still fairly broad. Today we're beginning the unit on convergence, so let's go ahead and do the normal thing. This is MAC2312.004, which is Calc 2. And the date today is the 9th of February, 2022. So exam 1 will be graded by next Monday. That's my usual rules, 1 week from the day you take the test. And today, let's clear up. Today we're going to talk about improper integrals, which is section 7.8 in your textbook. Now, I've never told you what a proper integral is, so to say we're going to talk about an improper integral is maybe not the clearest or most useful bit of information in the world, but we'll get into it. The only thing I want to say is that this begins, so today begins our discussion of this concept called convergence. And loosely speaking, so some vocab, right? This is not an English class, so I won't spend too long on this. But the word converge, besides being an excellent 90s hardcore punk band, is a verb, which in mathematics, right, in regular English, converge means to come together. In mathematics, converge means you have, it's a verb for an infinite process leading to a finite result. That's what we mean in math when we say the word converge. So I can say that this thing converges, right? And that means that this thing somewhere in it has an infinite process, and that infinite process was like nice or successful, led to a finite, clear result. There is an adjective form of this word, convergent, which is an adjective. And this is just the descriptor for a thing which is which converges. So and the antonyms, oh, I'm going to spell antonym wrong for these, are diverge and divergent. So the opposite of converging is diverging, and the opposite of convergent is divergent. That's all. Okay, and we're going to study a bunch of different objects that can have these words apply to them, right? Improper integrals, the things we're talking about today, can converge, they can diverge, meaning they can be convergent and they can be divergent. We're also going to study sequences. Sequences can converge or diverge. We're going to study series, which can converge or diverge. And we're going to study power series, which are a special kind of series that also have this notion of converging or diverging associated with them. Each one of these objects will have a different specific meaning. So when I tell you that an improper integral converges, that's going to be a slightly different meaning to what I mean when I say a sequence converges. But loosely speaking, these will always be the meanings, right? So loosely speaking, if you have an infinite process leading to a finite result, then that's convergence. And if you have a thing which does that, then I will call that convergent, whether we're talking about a sequence or a series or an integral. Okay. So I think the easiest way to get started here is to say this. And I'll say, imagine you want to calculate the area under the curve f of x equals 1 over x squared to the right of x equals 1. This is slightly different. Antonym. Yeah, it's like the opposite. Sorry. And I'm probably spelling it wrong. I may even be using the wrong word here, but opposite. You could just say opposites of these. The difference between the thing we're asking to find here and the sort of things that we found before is that I'm not saying I want to find the area under this curve from 1 to 2 or from 1 to 5. I want to find all the area under this curve to the right of x equals 1. So in terms of pictures, one thing about this code, my hand has been shaky lately. I'm having a hard time drawing straight lines. In terms of pictures, here's what we're trying to do. Here's the graph of 1 over x squared. It's got another piece on the other side here that looks like this. But I don't really care about that piece because I'm just trying to find all the area to the right of 1. So if I wanted to find the area from 1 to 2, I would integrate from 1 to 2. If I wanted to find the area under this curve between x equals 1 and x equals 3, I would integrate from 1 to 3. But I said I want to find all that area. And this goes on and on and on forever, right? This region extends infinitely to the right. Yeah, like if you were to look way over here, there would be a very short part of it, right? But there would be, the graph would still exist over here, and it would just be very close to the x-axis, and there'd be a little thin sliver of area there. There's a problem with this. So first, intuitively, we might say that this area is the integral from 1 to infinity of f of x dx. That has, I think, some intuitive appeal, right? I want to find all the area to the right of 1. So my lower bound of integration is 1, but then instead of stopping at like 3 or 5 or 7, I want to go all the way out to infinity. There is a problem here, though, and it's a little bit on the subtle side. Every time you've calculated an integral for me in this class, you found an antiderivative. Right? Every time you calculate an area or a definite integral, you found an antiderivative and then you plugged in the bounds. Doing that process of finding an area by calculating an antiderivative and plugging in bounds, that's the second fundamental theorem of calculus. So I'll say recall that the fundamental theorem of calc part 2 says that the integral from a to b of little f of x dx is capital F of b minus capital F of a, where capital F primed is little f, where capital F is an antiderivative. I don't know if your Calc 1 class proved that theorem. Not every Calc 1 class does. But if you look at the proof of the fundamental theorem of calculus, or if you think back to what you were doing earlier in chapter 5, it all came from Riemann sums, right? It all came from thinking about rectangles in there. And the starting point was to take the integral from a to b and to chop it up into n equal length subintervals and then construct a rectangle on each of those subintervals. The reason these integrals are called improper, and the reason why they require some special treatment, is because you cannot build a Riemann sum for them. So the proof of that theorem, the proof of FTC2 came from Riemann sums. Came from writing the integral from a to b of little f of x dx as the limit n going to infinity of the sum sigma I from 1 to n f of xi times delta x. And your xi, you might have had xi star depending on the sample points your professor used. But this is sort of the simplest way to write it, where delta x was the width of one of your rectangles, that's b minus a over n, and your xi's, if you're using right endpoints, was a plus I times delta x. Okay. So the second fundamental theorem of calculus, which is this thing that you can calculate a definite integral as values of the antiderivative, came from thinking of the definition of the definite integral, came from writing the definite integral as a limit of a Riemann sum, and then doing a bunch of clever work, right? It involved the squeeze theorem and some inequalities and stuff. What about this process could we not do for the black integral at the top right? So this is a question I want to ask you. I want you to think about it for a second. Right, because I think it's pretty intuitively satisfying to say that this pencil shaded area should be the integral from 1 to infinity. It's the area under f of x from 1 all the way out to infinity. And that's correct. Right? This is the notation that mathematicians would use to describe this. There's nothing wrong with that notation or that thinking. But there is a problem with the machinery that runs in the background when you do that. When you do trig sub, use sub, IBP, all that shit, you're finding an antiderivative, which means you're using FTC2, you're using the fundamental theorem of calculus. And I claim that the fundamental theorem of calculus does not work for this thing, which means all of our integration skills are useless here unless we can find a workaround. But before we talk about that workaround, I just want to see if we can identify where in here things go wrong for integrals like this. Think about it for a minute. See what you come up with. Yeah. So I've got a few things in chat here that I like a lot, right? Certainly the upper bound being infinity, that's the thing that's different. So if you try to take this recipe here and plug in infinity for b, that means you're plugging in infinity for b here. A would be 1, right? N is a variable. You're going to send n to infinity at the very end. But for now, b would be infinity and a would be 1. N would just be n. So infinity minus 1 is infinity. And infinity over n is infinity. So this piece, delta x, would be infinity. What happens if you take a rectangle whose base is infinite? What's the area of any rectangle whose base is infinite? Even if the height is like 0.0003, infinity times 0.0003 is infinity. If you try to set up the Riemann sum for this in the normal fashion, every rectangle would have infinite area. There is no way, right? The reason delta x is defined to be this is because you're taking the interval a to b and you're chopping it up into finitely many equal length subintervals. Since the interval from 1 to infinity goes all the way off to infinity, there is no way to chop it into a finite number of equal length subintervals. Either one of the subintervals has to be infinite in length, or you need infinitely many subintervals. There's no way to do the normal Riemann sum thing here. It can't be done. And while that might not seem like a big deal to you because you haven't had to calculate Riemann sums for any of the integrals we've been doing, every time you use the fundamental theorem of calculus, every time you calculate an integral by finding an antiderivative and plugging in bounds, that's what you're doing. It's just that this theorem does it for you. This theorem says that that integral really is this limit of Riemann sums, and that Riemann sum really depends on delta x being a finite number. And for an integral like this, delta x cannot be a finite number, which means we're boned. No fundamental theorem of calculus for any integral that looks like this. And that means no u sub, no integration by parts, no trig sub, no none of it. So what do we do? So for the completeness of your notes, the answer here is that delta x would be infinity, and we can't construct a Riemann sum. So FTC is gone. Right? If FTC leans on Riemann sums and you pull the Riemann sum away, FTC falls over. No more fundamental theorem of calculus. How do we fix this? We can get around this by being clever. Mathematicians just love that word, clever. Instead of going after all the area at once, I'm going to find a formula for the area, not from 1 to infinity, but from 1 to some variable. And then once I have that formula telling me how much area there is under this curve from 1 to, say, t, I can take the limit as t goes to infinity. And that's the game. I'm going to use the notation that your textbook uses here, although it's not my favorite. I'm just going to draw quadrant 1 because there's nothing important going on in quadrant 2 for this problem. Again, I will shade in pencil the stuff that we're after, but then I will shade in pen our little clever trick. So the pencil shaded area is the area that I want. Thinking strategically, that's what I'm after. This is what I'm after, but cannot build a Riemann sum for. So instead, I'm going to pick a letter to use, and I'll use T. The understanding that T is positive real number bigger than 1. And I'll find a formula for the purple area. Call this A of t, which would be the integral from 1 to t of f of x dx. God damn it. Dx, not dt, dx. Then the total area, the total like pencil shaded area, would be what happens as t goes to infinity. And since a of t is the integral from 1 to t, this is the limit as t goes to infinity, integral 1 to t of f of x dx. That's how we do it. Because we're assuming that t is a finite number when we come up with this formula for the purple area, that is not an improper integral. I can take the interval from 1 to t and chop that up and make a Riemann sum, no problem. So this integral here, the integral from 1 to t of f of x dx, is a regular Riemann integral. You can do all the regular things, including, your u sub, trig sub, IVP, whatever. Once you have that formula, then you send t to infinity. So the order matters. That's the trick. Okay, and this will get us around that problem. So the lack of an ability to construct a Riemann sum is why we call these improper. And we can fix the problem by kind of solving a simpler problem first. Instead of going straight after the area from 1 to infinity, get the area from 1 to t, use your normal tricks for that, then send t to infinity and get the total area. So having talked about this, let's go ahead and see if we can solve the problem that we started with. I have a picture that we can interact with just a bit over here in Desmos. So here is the graph of 1 over x squared. And what I've done here is I've just included a thing to measure the area up to t. So this is right the purple area from our thing here, right? What we're going to do is find a formula for this thing, the integral from 1 to t, and then we're going to send t off to infinity. What I wanted is all the area under there, and if I have a formula that gives me that purple area, then I can take the limit and see what we get. I'll make that Desmos environment available to you guys. But first, let's see if we can do it on paper. To evaluate the integral from 1 to infinity of 1 over x squared dx. And the way I do that is by writing it as the limit t to infinity integral 1 to t 1 over x squared dx. And now this integral is a normal Riemann integral. I can do the normal thing where you find an antiderivative for this function and then plug in the bounds. So an antiderivative for 1 over x squared, remember that's x to the negative 2. So this is limit t to infinity. Antiderivative for x to the negative 2 is negative x to the negative 1, or negative 1 over x. It's a power rule integral, right? It's just a power rule. I still have to plug in my bounds, and then at the very end, I have to take that limit. So I have now limit t to infinity, negative 1 over t minus negative 1 over 1, which is lim t to infinity minus minus makes positive. So this is 1 minus 1 over t. What is the limit as t goes to infinity of just the 1 over t piece? Forget everything else. What does this guy do as t gets bigger and bigger and bigger? Yeah, it goes to 0. That's correct. So 1 over infinity is always 0. In fact, there's a theorem in Calc 1, and we're going to be using so much of this stuff. So you remember in Calc 1, you learned about limits at infinity. Let me just describe off to the side here. It's a theorem from section 2.6 in the textbook, which says, I'll write it in terms of variable x. Limit as x goes to infinity of 1 over x to the p is 0 for any positive number p. So 1 over t is like 1 over x to the 1, right? So as t goes to infinity, this piece goes to 0. So we get here is 1 minus 0, and on a good day, that's 1. So in other words, how much area is there under 1 over x squared to the right of x equals 1? That area is exactly 1. And if you return to Desmos over here, if you look at this, the number in the little gray box here is the integral from 1 to t of f of x. So if I let t get really, really big, instead of just going out to 25, let's go out to like 1,000. And zoom out a little bit, you can sort of watch this happen. It's pretty cool. Watch this number getting closer and closer and closer to 1. Now we don't go all the way up to infinity, we're just going up to 1,000 here. But when you integrate from 1 to 1,000, you get 0.999, which is very, very close to 1. So as this number goes to infinity, this integral really does come out to 1. And I think it's fun to play with the slider here and just watch the area grow and see how the numbers up top change as that happens. So I'm going to, oh, I'm not logged in, am I? Log in. Let's save this for you guys. And then if you won't, you can play with this. So here's in chat. Here it is. Okay, but formally on the paper, this is how you need to do it, right? So you write this as the limit of the finite integral, calculate the finite integral, and then at the very end, take that limit, and whatever you get out, that's your answer. And you may remember that limits don't always come out to numbers. Sometimes limits like this come out to infinity, right? Like the limit as t goes to infinity of t squared would be infinity. And some limits don't exist, right? Maybe the left and right limits don't match, or you get some rapid oscillation or something like that. So it's not always going to be the case that when you run through this procedure, you get a nice number out at the end. And that, ladies and gentlemen, is where these words come back. That integral, that was an infinite process, right? I had a finite integral, but then I took the limit as the upper bound went to infinity. If that infinite process leads to a finite result, then I say that what happened there was convergence. The integral converged. And so I would classify that integral we just looked at as a convergent integral. If that limit fails to exist or comes out to an infinite number, then I would say that the corresponding integral diverges or is a divergent integral. So let me go ahead and give you the formal definition. These things that we're playing with are called type 1 improper integrals. There is a type 2, and they have slightly different rules. We'll talk about them as well, but let me go ahead. So a type 1 improper integral is an integral of the form like integral a to infinity f of x dx, or integral negative infinity to a f of x dx. Or let me call this a b here. We'll do it like that. You could also have an integral from negative infinity to infinity, and I will show you how to handle those. But for now, let me just focus on these two. So an integral of this form is where f is continuous, either on a to infinity for the first one or negative infinity to b for the second one, are called type 1 improper integrals. I'll just say type 1. They're defined as integral from a to infinity of f of x dx defined to be equal as the limit as t goes to infinity, integral a to t, f of x dx, that's the first guy, or integral negative infinity up to b of f of x dx, that's defined to be equal to the limit as t goes to negative infinity, integral t up to b of f of x dx. So if you're given an integral that looks like one of the two at the top, then the way you compute them is by writing them as limits of proper integrals, as I've done here at the bottom. Any questions on the notation? I'd like to point one thing out, and that's the continuity requirement. These functions need to be continuous. Not everywhere, right? Like 1 over x isn't continuous everywhere, it blows up at 0, but they need to be continuous over the interval that you are integrating on. So if I'm integrating from 1 to infinity, f needs to be continuous from 1 to infinity, or at least not have any infinite discontinuities. We say, and what I'm about to write here is true for all improper integrals, not just type 1 integrals. We say an improper integral converges provided the limit defining it right, the limits here exist and are finite. So the word we're defining here is converge, and we're defining convergence for an improper integral. If either of those are not true, if either of those conditions aren't met, we say the improper integral diverges. Provided. Yeah, the word right after converges here is provided. I'm bad about dotting my I's. I just like tap the page and these pens don't always get it. Okay. So I started by looking at the integral of 1 over x squared. You might ask, why not start by looking at the integral of 1 over x? Let's do that. One over x, very similar function to 1 over x squared. Graph looks very similar, slightly different symmetry, but same sort of stuff. Let's say evaluate the integral from 1 to infinity of 1 over x dx. And I think it is wise. Oh, sure. Sorry. Yeah, there was a lot to write there. I'm sorry. Here we go. All right. So what I was going to say is it's always nice to look at the graph. right? And that's why I give you that Desmos environment. If there's an integral you're looking at and you're not familiar with the graph, you can put it into that Desmos page and it will give it to you. But for things like 1 over x and 1 over x squared, those are graphs that we should know. And I think it's always nice to just give a quick sketch and see. We'll start to look for patterns, right? Mathematics is all about pattern recognition. So here I have the graph of 1 over x. I'm just drawing quadrant 1 there, but quadrant 2, it looks like this. There's a vertical asymptote here at x equals 0, but he's not involved in this problem because I'm integrating from 1 to infinity. So the area I'm after is the area under this graph everywhere to the right of 1, very much like the last one. But this graph is slightly different. The 1 over x squared graph is a lot flatter over here. Let me show you. So here's 1 over x squared. Turn off the purple, just see the graph. Here's 1 over x. Oh, I should move it green as well. Make this blue or something. Yeah. So you see the blue graph is not as flat as the green graph over here. The green graph, like 1 over x squared graph, he settles down on his asymptote a lot faster than the blue graph does. But it's still the same basic shape and the same basic question and the same techniques. So if I want to find all of that pencil area, I drop my parameter t over here, and I find a formula for the area from 1 to t, and then I take the limit as t goes to infinity. So the integral from 1 to infinity of 1 over x dx is defined to be the limit as t goes to infinity of the integral from 1 to t of 1 over x dx. That's from the definition that we just had up. The antiderivative step here is not hard, and you'll find in most of these problems the antiderivative step is not terribly hard, because it's really more about the convergence. Antiderivative for 1 over x is the natural log of the absolute value of x. So this is ln absolute value x, and it's a definite integral, so we're going to evaluate from 1 to t. I'll plug in the bounds and then try to take the limit. I get lim t to infinity, ln absolute value of t minus the ln, the absolute value of 1 is just 1, so I'll just write the ln of 1. What is the ln of 1? This has popped up a few times for us. Yeah. I like the subtle answer mechanism there, Elijah. That's good. Yeah, the natural log of 1 is 0. So really, we're just looking at the limit as t goes to infinity. And remember, t we're thinking of as being a number bigger than 1. We're sending it to infinity. So t is positive for sure. I'm not interested in negative values of t. So I can ditch the absolute values there as well. This is just the limit as t goes to infinity of the natural log of t, minus 0, which is just natural log of t. What is that limit? This is a slightly weird one. Yeah, the natural log function grows very slowly, but it is unbounded. So here I'll draw y equals ln of t. This is my t-axis. Natural log has a vertical asymptote at t equals 0, and then he grows like this sort of concave down growth, but it is unbounded. It's incredibly slow growth, right? The natural log grows as slowly as the exponential grows quickly, but it is unbounded. So this is infinity. Another way of saying this, if you want to think kind of in line with the theorem I gave you before, you can just say it in really simple terms. The natural log of infinity is infinity. Can't get this landscape to draw nicely. Okay. So that means I would refer to this original integral as divergent, right? We said if the limit defining the integral exists and is finite, the integral converges. If either of those conditions are failed, then the integral is divergent. So here there isn't a number, right? The answer to this question is not a number. We would say this integral diverges. And there's sort of a whole thing. You could say it diverges to infinity if you're feeling fancy, because there are other ways to fail to converge. But just telling me the integral diverges is sufficient here. You don't need to go beyond that. And again, it's not a terribly complicated integral, but the limit work at the end, that stuff from section 2.6 in Calc 1, is very important here. That's what we're leaning on, because the way we get around the issue with the Riemann sums is writing as a limit, and then at the end you got to take a limit. Wait, I want to show you as many examples as we can fit into class. We have finite time. Is there anything you'd like to ask or say more about this problem before I move on? All right, then. I'm going to do one more like this, and then we're going to talk about something slightly different. We'll get the integral from -1 to infinity of x over x squared plus 1. This graph is, again, not a graph that that I would require you to know, but it is a nice graph. It's called the Witch of Agnasi. Oh, no, that's 1 over x squared plus 1. This is called serpentine. Serpentine. Horizontal asymptote, y equals 0. And does something like this. -1 would be somewhere around here. What I'm looking for is all the area from -1 to infinity under this graph. So that's this negative area together with all of this positive area. Going on forever. Again, the only thing we can do here, this is the graph. The only thing we can do here is write the limit, write the integral as a limit, and then try to calculate. So let's do it. I'll just start up here. So this is equal to the limit as t goes to infinity, integral from -1 to t, x over x squared plus 1 dx. And now we focus our attention on the integral. It is crucial that at every step you write this limit. Okay, one of the common things that I am forced to take points off for on exam 2 is sloppy notation. So this first step where you write the original integral as a limit of an integral with finite bounds is necessary, not optional, necessary. You must do this. Don't get sloppy about this. And at every step, you need to write this limit until we're done. I know it means you're going to write a little bit extra. I have calluses too. It's okay, right? It's just like guitar players are very proud of the calluses on their fingers. Math people, get proud of this one. Right? It's all right. It's not bad. We're going to have to write a lot. That's okay. So we're going to focus our attention on this integral for the time being, but we're going to be good about our notation and continue writing the limit as we go. How do I do this integral? Very good. Yeah, it's U sub or Z sub, whatever you want to call it. Yep. What are we going to sub for? Excellent. We're going to sub for the bottom. So I'll tuck that substitution over here. I'll use the symbol Z. We're going to sub Z equals x squared plus 1, which means dz is 2x dx. You still need to change your bounds. This is a definite integral, and we're making a substitution. So again, don't get sloppy. When x is equal to -1, z would be -1 squared, which is 1, plus 1. So that's 2. And when x is equal to t, right? Our new bound here is t. We can't just use infinity. When x is equal to t, z would be t squared plus 1. So that's the substitution. And then when I plug that in, I'll still have limit t to infinity out front. This new integral is going to run from 2 to t squared plus 1. The x squared plus 1 downstairs, that's just going to be a z. All right, 1 over z. And then x dx is 1/2 dz. So I'll have 1/2 dz like this. I can pop the 1/2 out. Let me continue this over here. I can pop the 1/2 all the way out, not just out of the integral, but out past the limit as well. Remember, one of your rules for limits is that constant multiples can come out of those, just like they come out of integrals and derivatives. So this 1/2 can pop out front of the integral and then out front of the limit. So I have 1/2 limit t to infinity integral from 2 to t squared plus 1 of 1 over z dz. The antiderivative we use for 1 over z is the natural log of the absolute value of z. So this is 1/2 lim t to infinity. Natural log absolute value of z evaluated between 2 and t squared plus 1. Which is 1/2 limit t to infinity. Natural log of t squared plus 1 is always positive, right? T squared, you square a number, that's always greater than or equal to 0. Add 1, you get something strictly positive. So I don't need to worry about absolute values there. And then we subtract from this the natural log of 2. Everybody with me so far? All right. Now, as t goes to infinity, t squared goes to infinity squared. You square a big ass number, you get another big ass number. You add 1 to a big ass number, it's still a big ass number. So this piece is going to be the natural log of infinity. This is 1/2. I'll write it like that. There's nothing wrong with this notation. Natural log of infinity minus the natural log of 2. And from the blue theorem on the previous page, the natural log of infinity is infinity. This is 1/2 infinity minus the natural log of 2. The natural log of 2 is not infinity. That's just a number. In fact, I can't believe I say this, but it works. People tend to have a hard time remembering certain constants, but this is 0.69. The only way it could be better is if it was 420 afterwards, right? So the natural log of 2 is about 0.7 or 0.69. You can remember it that way. Infinity minus a very small number, a number like 0.69, is still infinity. And if you multiply infinity by 1/2, that's still infinity. So this is infinity. In other words, this integral diverges as well. Or we could say that the integral is divergent. But again, there's no numerical answer for this. Okay. Take your favorite function, right, and try to integrate it from 1 to infinity. See what happens. The way I would like you to be thinking about this, let's come back to Desmos for a minute. So far, every problem I've given you, when you look at the graph, they all have one feature in common. This graph, both of the graphs up in Desmos have a shared feature. What's that shared feature? Here's the purple guy. Make him red or something. What do you notice about these? What are they all doing here? Forget about this stuff. I don't care about this stuff. I'm integrating from 1 to infinity. What matters is happening out here. They all have the same horizontal asymptote. They're all going to 0 eventually, right? As you cruise out here on this graph, all of them, any of them, they all go to 0 eventually. You notice the green graph goes to 0 much faster than the red graph or the blue graph, right? He's way down here, they're up here. The integrals of the red and blue function were both divergent. That area was infinite. The integral of the green function was convergent. That area was finite. That's not a coincidence. So when I say I want you to draw the graphs and think about what's going on a little bit, look for patterns. One of the patterns is that all of the functions that are worth even trying to integrate like this from 1 to infinity, or from wherever to infinity, they all go to 0. That is a necessary condition for the integral to converge. For an integral to even have a chance of converging, a type 1 improper integral, the function needs to go to 0. If the function, imagine the function didn't have horizontal asymptote y equals 0, had something else like y equals 1 as a horizontal asymptote, then the area under that, you could squeeze a little rectangle in there with infinite width and height 1, which means that area obviously infinite. So having the horizontal asymptote y equals 0 is a necessary thing. When you think about functions that have that horizontal asymptote, let's write some of this down. This goes into the notes. All type 1 improper integrals which converge have integrands f of x with horizontal asymptotes, or horizontal asymptote y equals 0. This is necessary, but not sufficient. For the integral to converge. Right? If the function doesn't go to 0 as you go off to the right, then there's no way the area could be finite. Looking just at the green function for a minute. Really, all the cool shit is happening early on. Like, change this to something like. Pretty much all the area is right here. Yeah, like this is the vast majority of the area. There's not a whole lot that comes from the tail. As you go further out, there's really very little contribution past, like, say, 50 or so, 20, 25, whatever. As you step further and further out, there's just this tiny little slice of shit out here. There's very, very little. Really, all the area is back here. So what matters here is the function going to 0 and going to 0 very quickly, so that there really isn't much out here, because the stuff past here is infinitely wide. So in order for it to be finite in area, it has to be extremely short, like really short. Like 1 over x isn't short enough. It needs to be like 1 over x squared. And when I mention this note, what I'd like you to do is think about what kind of functions, if you think about all functions that have horizontal asymptote y equals 0, there's a particular family of them. There's a particular family of them that are kind of archetypal of that behavior. Are we looking for this page again? So yeah, infinitely long is a valid response, and approach 0 is really what we're looking for here. All the functions that even have a chance of yielding convergent integrals must approach 0. And that's what we're saying here. But 1 over x approaches 0, his integral still diverged. So it's not enough. It's necessary, but not sufficient, right? And that's what that means. It means without this thing, you're fucked. But having this thing is not a guarantee. And when we think about the functions which do this, one big class of functions like this are reciprocal power functions, right? That was that blue theorem earlier. 1 over x to the p always goes to 0 as x goes to infinity. Integrals of the form, this is a definition now. Integral from a to infinity 1 over x to the p dx are called p integrals. They're all type 1 improper integrals. A here is assumed to be a positive number. Often we just say 1 to infinity, but you can say a to infinity where a is any positive number. These are called p integrals. And what I would like to do in the last few minutes of class here is prove for you exactly when these converge and exactly when these diverge. We've seen that the integral of 1 over x diverges. The integral of 1 over x squared converges. Let me return to Desmos and show you just a few more so we can start to get a sense of what to expect. Okay, here's 1 over x. And yeah, the area under 1 over x is going to be a lot bigger because 1 over x is a lot bigger. 1 over x squared is already there. How about 1 over x cubed? Oh. So the black function is even smaller. So if you integrate that one from 1 to infinity, you get a finite area as well. What about 1 over x to the 1/2? That's 1 over the square root of x. He's even bigger than the blue guy. And the blue guy, the area under him was infinite. So all of these have that asymptotic behavior. They all go to 0 as you go out to the right. Somewhere here, there is a tipping point. If you look under 1 over x, divergent, right? Too much stuff. 1 over x squared, that was convergent. 1 over x cubed, well, this is even smaller than 1 over x squared, so that'll be convergent. But somewhere there is a tipping point. And that's our last theorem for today. P integrals converge if p is strictly bigger than 1, and diverge if p is less than or equal to 1. So integral of 1 over x squared, 1 over x cubed, 1 over x to the 4, done from 1 to infinity, those are all convergent. Integral of 1 over x, 1 over the square root of x, 1 over the cube root of x, all of those done from 1 to infinity, divergent. I am actually going to prove this for you. It's not a hard proof. Suppose p is bigger than 1. Then the integral from a to infinity of 1 over x to the p dx is, by definition, limit p to infinity, integral of a to t, x to the, already there's negative p dx. Right, 1 over x to the p, that's x to the negative p. And the antiderivative for x to the negative p is x to the negative p plus 1 divided by negative p plus 1. And this is to be evaluated from a to t. The negative p plus 1 downstairs is a constant. It doesn't have any x's in it. It doesn't have any t's in it. P is a constant. And P is just a constant, I'm assuming is bigger than 1. So I can pull that piece out. That's 1 over negative p plus 1. And come all the way out past the limit, just like our 1/2 did in that earlier problem. And then I have left here limit p to infinity, x to the negative p plus 1 evaluated from a to t. If I rewrite this now, right, because having a negative p plus 1 power, that's a little bit weird. Over here, I'll also do a little rewriting. Negative p plus 1, that's 1 minus p. Looks better like that. And then p to infinity. If I want to bring this guy downstairs, the sign is flipped. So this is 1 over x raised to the p minus first power, evaluated from a to t. And now I'll just plug in P and I'll plug in A. This is 1 over 1 minus P times the limit as P goes to infinity of 1 over T raised to the P minus 1 power minus 1 over A raised to the P minus 1 power. This piece is finite. A is just a constant, right? Like we usually integrated from 1 to infinity. This piece is finite, and it's independent of the limit. This piece is the piece we need to think about. The limit as P goes to infinity of 1 over P raised to the P minus 1. This is another one of those limits like the blue limit we looked at, right? It's 1 over your variable to some power. The power here isn't just P though, it's P minus 1. So the question is this power positive or is it negative? If this is positive, like 1 over T squared or 1 over T cubed or 1 over T to the 0.12345, then this limit would be 0. If this power is negative, then this term really belongs upstairs, and this limit would be infinity. But what do I know about P that will let me figure out whether P minus 1 is positive or negative? What assumptions have I made about P? Look around on the page. Is there an assumption about P anywhere? Very good. Yeah, thank you. We made the assumption here that P is bigger than 1. So if P is bigger than 1, subtract 1 everywhere. That means P minus 1 is bigger than 0. So this limit is 0 because P being bigger than 1 implies P minus 1 is a positive number. So this limit down here is 1 over 1 minus P times 0 minus 1 over A to the P minus 1, which is finite. And that's it. We're done. If P is bigger than 1, then this integral comes out to this finite value. Therefore, the P integral A to infinity 1 over x to the P dx converges. We've already shown that the integral of 1 over x to the 1, if you take P equal to 1, that is divergent. And if you assume that P is smaller than 1, then this number would be negative. So that's really the proof. That's really the whole game. We've already seen that if P equals 1, the integral A to infinity 1 over x to the 1 over x, right, dx diverges. So the only thing we need to still show that the integral of 1 over x to the p dx from a to infinity diverges if p is less than 1. And that's not hard, but I'm not sure. Nah, I've already taken you over time. But this follows similarly to the p greater than 1 case, because we'll still have integral a to infinity 1 over x to the p dx equals then p to infinity x to the negative p plus 1 over negative p plus 1 from a to p, and that would still be 1 over 1 minus p, then p to infinity 1 over x to the p minus 1 minus 1 over a to the p minus 1, okay, p. But now p minus 1 is negative. So this piece goes to infinity. And that really is the whole truth. Oh, there's a fun question in chat. What about stuff like 1 over e to the x? Yeah, we haven't seen anything quite like that. So let me first go ahead and say we're over time already. You guys can leave if you want to leave. Right, class is done. Next time, I will look at some more examples of type 1 integrals. We will introduce type 2 integrals, and then a theorem that will help us compare one integral to another integral. Elijah, for your question, there's a few good ways to answer this. And some of them, if you're comfortable thinking about the comparison type stuff, can go very fast. E to the x grows quickly, right? Much faster than x squared or x cubed or any of those. So 1 over e to the x goes to 0 very quickly, much faster than 1 over x squared or 1 over x cubed. So the integral of 1 over e to the x is going to be smaller than the integral of 1 over x squared, and therefore convergent. To actually see it out, if you want to integrate, say, from 0 to infinity, 1 over e to the x dx, this would be ln e to infinity, integral 0 to p, e to the negative x dx. Right? 1 over e to the x is e to the negative x. And that would be ln e to infinity, negative e to the negative x, evaluated from 0 to p, is ln e to infinity, negative e to the negative p, minus negative e to the negative 0, which is then e to infinity, 1 minus e to the negative p. And as t goes to infinity, e to the negative p goes to 0. So this would be 1 minus 0, which is 1. So that is a convergent integral. And anything you're curious about, you can always crunch it out, right? You can go ahead and write the integral, calculate your antiderivative, fill in the bounds, and then take the limit and see what you get. What it really comes down to is how comfortable you are with these limits. So if there's any place where we need to be careful, where we might need to go back and refresh ourselves, things like the squeeze theorem and L'Hopital's rule from Calc 1 are going to show up here because we're taking limits at infinity. So those would be places to refresh if you need it. I think probably everybody needs it. I will solve more complicated examples in class where we use things like L'Hopital's rule, and you'll have plenty of opportunity in the homework to work with integrals like these. But if you're struggling with anything, I would go back to section 2.6 in the book and make sure that those limit techniques are still there in your brain. The theorems I showed today from that section, like the limit of the 1 over x to the p thing and the natural log thing, those are all good, but of course there are many, many more problems there where you have to take limits as x goes to infinity, and we do need all of those techniques still here. So exponentials, there's stuff about the inverse tangent function, all of those sort of things we want to make sure we have nice and solid in our brain from that section 2.6. So that was here. starts on page 126, I guess, but really 127 where the stuff begins. All of this stuff for limits at infinity we will need. So it might be wise to go back and remember that. Here's the theorem that we spoke about earlier. This renormalization trick where you divide top and bottom by the largest power of x is good. You can apply that in more complicated situations. And then L'Hopital's rule, I think, has its own section here, which starts on page 304. And you might want to take a look at this as well. So that's it from me for today. Next time, we're going to talk about how to compare one improper integral to another. And we're also going to see a different kind of improper integral called type 2 improper integrals, where instead of having infinite width, you have infinite height. And those we can handle as well, but they require a slightly different approach. So I won't say any more here today. We'll pick this up on Friday. You have a homework set open. Please get in there and take a look at anything you can between now and Friday. And then on Friday, we'll talk about type 2 integrals and comparisons. Okay. Take care, guys.